today in the virtual BUL seminar series. Today our speaker is Chris Rattray, who is a student here at the School of Meteorology, a third-year student working with Dr. Dave Parsons. Prior to coming to the University of Oklahoma, Chris went to undergraduate at the University of Manitoba, where he earned a Bachelor of Science degree in physical geography with a specialization in atmospheric science. And today, Chris will be talking to us about the nocturnal low-level jet. So go ahead and take it away.
Okay. Thanks, Liz. So a lot of the results I'm going to show today are pretty recent. So if anyone notices I overlooked something, please feel free to point it out at the end. So nocturnal low-level jets are common over the United States during the warm season. They typically have a strong southerly component, which has been identified as an important source of moisture transport for the region. The need to better understand nocturnal low-level jets is motivated by their role in facilitating mesoscale convective systems, which can have a significant societal impact. And this work seeks to provide a better understanding of the mechanisms that control low-level jet formation and intensity and how they facilitate convection. So nocturnal low-level jets are typically defined as a wind maximum occurring several hundred meters above ground. And the figure shown below is what a typical southerly jet profile looks like. Climatology has found that they most frequently occur in Kansas and Oklahoma, as you can see in the figure on the right there. And several mechanisms have been proposed to explain this maximum in occurrences. There's still debate around the contributions from each of the mechanisms. However, the slope has been identified as a key factor in why this particular area is favorable. And here are 4 commonly used mechanisms to explain how jets form by boundary layer processes. First, the inertial oscillation or IO mechanism. This occurs when daytime heating shuts down and mixing ceases in the boundary layer, causes a disruption to the force balances, resulting in the wind vector to undergo oscillation around the geostrophic wind vector. Second, the thermal wind reversal along slope terrain, or a Holton mechanism. This takes place when the surface cools more quickly than upper portions of the boundary layer at night, leading to a thermal wind reversal, resulting in a low-level southerly geostrophic wind maximum. And this assumes uniform heating along the slope. The third mechanism is uneven heating along the slope. As a result of uneven heating along the slope, this causes a pressure gradient that changes with height, producing a southerly geostrophic wind maximum. The fourth mechanism is due to mean seasonal heating along the slope. This creates a southerly geostrophic flow. Southerly jet results from the IO mechanism superimposed on the southerly background flow. To help explain this southerly wind maximum, Shapiro et al. Combined the Blackadar and Holton mechanisms in an analytical model to produce, this is found to produce southerly jets closer to those observed in the United States Great Plains. Their results also showed a westerly maximum occurring above the southerly jet. This westerly jet has been associated with convective initiation in subsequent work. It has been found to be associated with creating a more favorable environment for MCSs by increasing convective available potential energy, or CAPE, and reducing convective inhibition, or SIN, aloft. The westerly jet has also been found to advect the daytime boundary layer from the higher trend to the west, which causes changes to the buoyancy gradients and can further alter jet structure. Given the complex nature of the low-level jet, this work will take a step back and examine how they return to the region after a cold front comes through and knocks out the necessary conditions for their formation. In doing so, this work will provide a synoptic framework for the low-level jet by examining their day-to-day evolution as they return and which processes are controlling their formation. This work will also investigate the role in returning unstable conditions to the region by examining the spatial and temporal evolution of CAPE and SIN. So the primary source of data comes from 3-hour radiosonde data taken from the IHOP 2002 field campaign. It took place from May 13th to June 25th, 2002. And the configuration of these sites allows for the calculation of gradients over Lamont using finite differencing technique. And this is supplemented using ERA5 reanalysis data from the European Center for Medium Range Weather Prediction. So there were 3 cold fronts during the period. This work will mainly focus on the days between the 2nd and 3rd front. So that's June 5th and May 13th. So just taking a quick look at the evolution after the first front. So this is showing the V component. Closer to the first front, we see a weaker southerly max that increases in later days after the front. Looking at the evolution after the second front, we see a similar thing where the southerly jet increases in later days. Westerly jet again shows a similar pattern where we see intensification later on. And same thing for after the second front. So to better understand this evolution, we begin by looking at how the southerly winds evolve. In this figure, the colors are the V wind at Lamont, and the contours are the ageostrophic component calculated using sounding data from other sites. And the black line is the boundary layer height from ERA5. So from this, we can see that there is nocturnal intensification, and we see the IO mechanism from the ageostrophic component, looking at the contours. And we notice that the southerly flow begins in the first day or two after the front. So just taking a look at the first day after the front, we see, first of all, previous work has found that soil moisture and vegetation differences along the slope contribute to the thermal gradients that drive the low-level southerly winds. And in this figure on the right, it shows theta V, surface theta V contours and soil moisture from the ERA5. And we see evidence of the gradient along the slope occurring further up in the panhandle. However, there's still not much of a difference between the western and eastern sites. as we can see in the profiles of theta V. And then when we just take a look at, this is showing a vertical profile of CAPE, we see that there's no CAPE. And so taking a look at the second day, we can see that the thermal gradient is beginning to return along the slope, and it's beginning to move into Oklahoma. And this is starting to show up in the profiles from the sites. We now see that Visay has a warmer profile than Morris. And this explains the increasing southerly flow. And however, we still don't have any CAPE at Lamont. So when looking at the southerly winds on the 8th, we see an intensification. So on the figure on the right, the top is what was shown before. And on the bottom, this figure shows southerly geostrophic wind as contours and the theta V gradient between the western site and central site. And so the redder colors in this figure mean that it's warmer at Lamont. And notice that on the 8th, there's an intensification that occurs where you have increasing geostrophic winds along with the buoyancy gradient reversal that occurs below 1 kilometer. So to understand what's driving the reversal, we look at soil moisture and theta V. Now this plot is showing soil moisture like before, except now the contours are showing the difference in surface theta V between 6 and 0 UTC. So they do show some overlap, but there's some areas where they don't. However, 6 hours later, so when you look at the difference in surface theta V between 12 and 6 UTC, you don't really see much overlap between soil moisture. So suggests that it doesn't offer a complete explanation for the thermal gradients. Just taking a quick look at the synoptic conditions, we see that there's little from synoptic scale influence with the upper level jet located in the northern plains, and over Kansas and Oklahoma, we have that southerly low level winds, which we would expect from the heating along the slope. And there's most of the moisture is still in Oklahoma, as you can see from the dew point contours. Just taking a closer look at the buoyancy gradient, figure on the left is showing the difference in theta V between Visay and Lamont on the 8th. And on the right are the theta V profiles from Visay and Lamont in height above sea level for the y-axis. And from this, we can see that the theta V gradient reversal happens below 1 kilometer. And it begins at 0 to 3 UTC. And Visay is cooling over a deeper layer than at Lamont. So when we look at advection of theta V to try and explain this, we see that there is some weak advection taking place at the height of the southerly jet. This is occurring after 6 UTC. So on the right, showing the advection, and the black line is the later time, so 12 UTC, and then lighter the line the earlier the time. So at 0 and 3 UTC, there's not much advection happening there. So just looking at this again, the top panel is the same as before with the theta V gradient. and the bottom panel shows the mixing ratios, the colors, and the contours are advection of mixing ratio at Lamont. So we see the greatest moistening occurred around the 8th, low-level moistening, and this was associated with the rapid increase, or the greatest increase in the geostrophic winds, and this so suggests they may be associated. And then when we look at the downwelling long-wave radiation at Lamont, we see that there's this sharp drop where we have that cold front on the 5th, and then it increases rapidly within the first few days. So that rapid intensification continues until the 9th. So now looking at comparing Lamont to another site, Coldwater, Kansas, which is located just to the north of Visay. We see that on the 8th, there's this time, or on the 8th, the two profiles show a divergence, and this doesn't occur at any other date in these times. Although there's some convection going on here, so. But so could this be contributing to that gradient reversal? So to look at this, here this plot shows a 6-hour change in sensible heat flux at the surface, and so that's the contours, and then the colors are the change in downwelling long wave at the surface, and this is from ERA5 data. From this, we see that the greatest decrease in long wave also corresponds to the greatest decrease in sensible heat flux, especially in Kansas. And now here the contours are showing the change in theta V at the surface, and we can see that the contours line up pretty closely with that drop in long wave. So this suggests that long wave may be driving the gradient in this case. So we noticed that the height where that cooling happened is around 700 meters above sea level, and it cooled by about -8 Kelvin. When we look at a theta V profile from Hillsborough, located just to the east of that cooling, so at the same height at Hillsborough, it cools by about 4 Kelvin. Just doing a quick thermal wind calculation, we find that it should have resulted in a change in the thermal wind by about 8 meters per second per kilometer. So then looking at the V wind profile at Hillsborough, so comparing 6 and 0 UTC, we see that dV/dz increased by about 10 meters per second per kilometer within the lowest 500 meters above ground. So just keep in mind the y-axis here is sea level. So that would be consistent with our thermal wind calculation if we also factor in the IO mechanism, which would contribute the ageostrophic component. So going ahead 6 hours, we see that the greatest decrease in downwelling long wave took place in this area in western Kansas, and it cools by about -5 Kelvin, and the height of this terrain is about 800 to 1,000 meters above sea level. Looking at the theta V profile at Hillsborough, we see that it doesn't really change that much at the same height. So doing another quick thermal wind calculation, this time approximated the distance is about twice as much as before. We see that it should have resulted in about a 3 meter per second per kilometer change. And looking at the wind profile, we see that it actually had a 6 meter per second per kilometer change up until 1 kilometer above sea level. And again, this is what we might expect with also the IO mechanism increasing the winds as well. So now these contours are showing the 6-hour change in the 0 to 1 kilometer mixing ratio from ERA5. So we see that in areas with decreased long wave, they were associated with a decrease in moisture. And so here the green arrows are showing the wind vectors and the height of the southerly jet. And they're suggesting moisture advection is contributing to the distribution. So this suggests that moisture advection by the southerly jet may act as a self-enhancing mechanism by keeping the sites to the east from cooling as rapidly due to decrease or not decreasing the downwelling long wave as much. You might expect that moisture advection has an impact on CAPE profiles, and this appears to be the case. So these profiles are showing CAPE as a function of height. The black line is 12 UTC, lighter lines are earlier. And we see that all sites have greater instability aloft at night with a northeast trend. So looking at this, looking more closely at the profiles, we see that there's, if we just focus on Lamont, we see that there's a spike at 2 heights. One occurred around 500 meters to 1,000 meters, and the other one around 1 to 1.5 meters above, or 1 to 1.5 kilometers above sea level. So taking a closer look at that change in CAPE. So looking at the mixing ratio, we see that it shows that pretty large increase aloft in mixing ratios. Also increases below, as we might expect with the low-level jet. But when we calculate mixing ratio advection, we find that it's not enough to account for the increase aloft. And this profile is consistent with ascent. So this SKU-T profile on the right is showing the 3-hour change. The solid line shows the parcel path at 9 UTC, and the dotted line shows the path for the same parcel at 6 UTC. The red line is the 9 UTC temperature. The purple line is the 6 UTC temperature, and the green line is the 9 UTC dew point, and the blue line is the 6 UTC dew point. So you can clearly see that there's a lot of moistening and cooling going on below 700 millibars. And that shows up when we look at the potential temperature profile. We see that it cools by about 5 degrees Celsius from about 1.5 to 3 kilometers. and when we calculate the vertical velocities at Lamont using sounding data, see that there's ascent of 2 centimeters per second. It does decrease around 9 UTC, but it appears like it's around 2 centimeters per second through most of the night. And this is consistent with what we saw in the cooling and moistening. And this is needed to explain that, since the advections were not enough to account for these changes. So just a quick summary of the first few days. So on the 6th and 7th, southerly flow was driven by heating long slope terrain. On the 8th, we had uneven heating along slope terrain due to differences in downwelling long wave. And these gradients were associated with changing moisture along the slope. However, these results are still very recent, and it needs to do more work to look at this, such as looking at the full energy budget and other things. And then unstable conditions returned to the region with moisture advection and ascent associated with the jet. So after the 8th, we see that there's these gradient reversals that take place without moistening that we saw on the 8th. If we look at the 10th, we notice a very prominent reversal around 1 kilometer and a negative reversal around 2 kilometers. We also see that there's negative moisture advection around 2 kilometers on the state. If we recall, I mentioned previous work by Smith et al. They found that the westerly jet could advect the dry boundary layer from the west and cause some buoyancy gradient reversals. So looking at theta V advection at Lamont on the 10th, we see that there's strong advection occurring at heights where we would expect a westerly jet. Just take a quick look at the synoptic conditions on the 10th. We see that there's a trough located just to the east of the Rockies, but notice how there's now a strong dry line in the panhandle, which you can see in the dew point contours on the right, in the figure on the right. And now all of the sites are located within that moist air mass during the day. So looking at what impact that might have on the downwelling. So this is again showing the 6-hour change in sensible heat flux at the surface, along with the change in downwelling long wave. We see that sensible heat flux is associated with or a decrease in sensible heat flux is associated with a decrease in downwelling long wave. And we notice that there's this area. Okay, first of all, now the contours here are showing the decrease in theta V at the surface, and now we notice that this area of decreased long wave is associated with a sharp gradient of cooling at the surface. And this is located around 800 to 1300 meters above sea level. Just taking a look at the V wind at Visai, we see here that dV/dz increases up until around the same height when compared to the earlier time. So this is consistent with what we found with the thermal wind from the previous date. And just taking a look at another site to the north at Hillsborough. Again, it shows the same change in dV/dz up until around that height. Now, these aren't the geostrophic winds, so all we can really say that it is consistent with what we saw before. Going ahead 6 hours, we see that the greatest cooling took place a little bit higher up along the slope. So the height of this train now is around 1.1 to 1.6 kilometers above sea level. And now I have the red arrows showing wind vectors at the height of the westerly jet. Taking a look at a theta V profile from VISI between 12 and 6 UTC, we see that around that height, there's not much change. It looks like it even warmed a little bit there. So when we thermal wind as before, we see that this height corresponds to where it increased up until, so it's still consistent with what we saw with the thermal wind. And just again at Hillsborough, see that there's still this increase in the dBdz at those levels. And this is showing the U wind. So just taking a look at the evolution of the theta V profiles between VISI and Lamont, they seem consistent with what we might expect from that Holton mechanism with the uniform heating along the slope. But since these results are still pretty new, I still have to look at this a little bit further to confirm this is what's going on here. So looking closer at this profile, we see that there are areas around 1 kilometer where Lamont cools more than VISI, and then above where Lamont actually warms up a little bit more than VISI. And this suggests there may be some advection taking place around 1 kilometer, keeping VISI to the west a little bit warmer than Lamont. And then we just take a look and see what changes, what were the changes to dBdz at this time, and it appeared the heights match up with what we would expect from changes to the thermal wind. So below it, actually the winds actually decreased, and aloft dBdz increased over the 3 hours. So to look at this a little bit further, I'm just going to go through a few cross sections using ERA5 data, and so the meridional and zonal cross sections intersect at Lamont. So now here, the black arrows are the geostrophic component of the wind, and the red arrows are the ageostrophic component. The pink contours are vertical velocities, and dashed are negative values, or so solid is positive and dashed is negative. And then the black line is the theta V contours, and colors are mixing ratios. So at 0 UTC, we see a deep dry boundary layer to the west, ageostrophic upslope component, and a dry line located around 101 west. And so just keep your eye on the geostrophic component around the dry line. We see that the geostrophic winds become more westerly with height as we step through the earlier times here. And again, it's the zonal thermal wind appears to be increasing. And this is what we might expect if moisture is associated with differential heating along the slope. As the moisture collapses along the dry line, it spreads out and may cause the changes in downwelling long wave and also the changes in the theta V. Now, as you'll see the boundary layer from the west advect eastward. So there's continuing some changes in the and the boundary layer is continuing to advect east. So we should continue to see some changes we should start to see some changes in the meridional profile at the bottom. It's nearing Lamont, marked by B in the panel on the top here. And now as it starts to approach Lamont, we start to see some changes happening in the southerly geostrophic winds. And the dry boundary layer is now being advected northeast. Now at 12 UTC, we see that we have much more moist air near the surface and an area of reduced static stability around 3 to 5 kilometers above ground. And this appears to be the result of moisture advection by the southerly jet, downslope flow of moisture from the dryline collapse, and advection of the dry boundary layer by the westerly jet. Now, just taking a look at what were the results to change it to the Cape profiles. As we expect, we see a north-eastward trend in destabilization overnight. Cape peaked at the western site around 6 UTC and later in the north. All sites gained more Cape overnight than at the 0 UTC time aloft, except the south. Take a closer look at the changes at Lamont. We see that Cape increased above 500 meters and SIN was reduced, and you can see the change in the lapse rates between the earlier and later times. And also, we see that there's moistening evident in the SKU-T profile below 700 millibars. And when looking at the vertical velocity and divergence, we see that we only start getting ascent to take place at later time. And this is consistent with what we saw with the westerly jet being taking place later at this site. So just to go over some of the findings from earlier, on the first day or two, we had southerly winds develop with the slope heating up faster due to vegetation and soil moisture. On the third day after the front, we had moisture advection by the southerly jet, possibly enhancing buoyancy gradients. And then we also, at this time, we also finally had unstable conditions develop. So now on the 10th, we had buoyancy gradients occur higher up along the slope near the location of the dry line during the day. As a result, all sites were under a warm air mass, warm moist air mass, and the effects of the holding mechanism have contributed to the southerly jet. But just like to emphasize, these results are still very recent, so still have to verify this. The characteristics of the southerly jet from 0 to 6 UTC were consistent with being influenced by the thermal wind effects from the changes to the thermal gradients along the slope. And from 6 to 12 UTC, the characteristics of the westerly jet were appear to be influenced by the cooling taking place further upslope in eastern Colorado. The westerly jet advected the dry boundary layer from the west, which appeared to alter the structure of the southerly jet. And that would be the end of it.
Thanks, Chris. So in order to keep this a little bit more organized, if you have a question for Chris, please go ahead and type in the chat box that you have a question, and then we can have an organized order of asking those questions. While we're waiting for anybody else to chime in the chat box, I have a general question. So particularly in the example that you were showing for the 10th of June, you were showing the change in the theta V and the change in the downwelling long wave radiation. But it looked like the way that in that map, the way that you were doing this, these were heights above mean sea level. And so how do we compare information? How do we compare information across the sloping planes if we're only considering height above sea level? Because the distance from the surface, which is what drives a lot of these things, is different.
I guess, so at this height, that is true. I would still expect it should still influence the thermal wind at the same height, or if I'm not mistaken, I could be. Yeah, that would be something to look at as well.
Yeah, I asked because some work that actually Alan, I think, has put out, and I think it's similar to what Josh has done as well, kind of puts forth this idea of the tilted boundary layer that, you know, follows the slope. And so you do have these gradients that in along mean sea level height coordinates, you know, they are exiting what we would commonly define as the boundary layer. Whereas if you're considering boundary layer flow and boundary layer advection, a lot of times these motions are confined to that sloped boundary layer. So when you cross it by looking at the mean sea level heights, you know, you're at some point exiting what we would think of as the nocturnal boundary layer. So it just makes some of these results a bit difficult for me to contextualize, because this slide in particular is quite similar to some of the things that I have done, but the results are a bit different because I was looking at it in a slope following coordinate system.
Yeah, and yeah, I guess that also that's kind of what I is trying to put them side by side on the same y-axis, so you could, I guess, more easily compare them. But yeah, these are still results from, I guess, last week or two. So I'd be happy to look more into what you're referring to. But yeah, thanks for pointing that out. Are
there any other questions for Chris? Chris, Dave has typed into the chat.
Yeah, Chris, there's a lot there, and like you said, some of it was pretty recently added. I noticed in one of your plots, and bullets, the VG was a maximum at the surface in the late afternoon. And this is ideas consistent with the work by Parrish and Josh and Allen and others, that you get a nocturnal low-level jet due to the Blackador mechanism on top of a surface-based geostrophic wind. But you're basically saying the thermal wind matters too, right? Because of this reversal. And the thermal reversal, just to follow up on it, Elizabeth Smith's excellent comments, the thermal reversal is, you didn't go into it here, but it's actually pretty complex, because late in the period, it actually extends into the development of the morning transition of the boundary layer. The boundary layers have such a different evolution on the slope, besides the, looking along the gradient on the slope. So basically you're saying the thermal wind variation during the night matters too. And it would be good to see that calculation for the second period. We just saw it to the first. So any comments?
Yeah, these are good points. As far as I can tell, they're consistent, but I do still need to look into that, quantify it a bit more, and yeah, I guess.
Can I quickly?
Can I make one real quick comment too, that there's a lot here and it wasn't really, everything couldn't be covered, but if there were plots that Chris has made that has the U total wind associated with the flow instead of the UG and AG separate, and you do get these two areas of convergence that move along with the westerlies aloft, one almost with a deep daytime boundary layer and one sort of down low, which is maybe more similar to what other people have talked about. Sorry to interrupt, Alan, go ahead.
Yeah, I quickly want to say, I mean, it's absolutely key to know whether we're looking at a constant height above sea level or MSL or AGL or 850 hectopascal surface, and all those are absolutely critical for what Liz has brought up. Some of the diagrams have information on a surface like a above ground level. And on that same diagram, there'll be other information on, say, an 850 hectopascal surface, which are obviously different. And the results are shown for different reasons, but on the same diagram. And so there's a lot of information there. And in a seminar, it makes it really hard to keep track of which fields are on which surface. I agree. We need to know what or to think about which levels are being shown. There's probably not enough time in a seminar to present all the information about which surfaces are being shown. In earlier versions of the talk, I saw that that there were multiple levels, pressure levels versus surface levles shown on the same diagram. I don't know if some of that information may have been left off of some of these more recent slides. But anyway, I agree. This is something we really need to keep in mind about, because it's a huge difference. So we need to keep that in mind. I agree with Elizabeth's comment.
One more comment to add on that, and then I'll promise I'll shut up. The fact that it's such a complex function of height, and later in the recovery period, the gradient's essentially aloft. I think that says maybe the idea of just always looking along the slope is perhaps not a good fit, because I don't see how looking along the slope is going to give you that complex function of height that's actually a maximum aloft later in the period.
Okay. Any last minute questions from the crowd? All right. If not, thank you, Chris. Thanks for this talk. And I guess we'll see you guys